This is your video for, your part 1 video for 6.4, the fundamental theorem of calculus. And so this section is going to show the discovery of the connection between integration and differentiation. So theorem 4, that's the first one we're going to start off with. This is the fundamental theorem of calculus antiderivative part. So there's two different parts to the fundamental theorem of calculus. Some books and some classes refer to these as part 1 and part 2, but usually they mix up like which one is part 1 and which one is part 2, depending on what textbook you're looking at. So this book has taken the approach of referring to these by what they do. So there's the anti-differentiation part, and then later on, we are going to look at the fundamental theorem, the evaluation part. And the evaluation part is actually what we did at the end of 6.3. So with the antiderivative part, if f is some continuous function on a to b, then the function, capital F of x is equal to the integral, has a derivative at every point x in a to b, and the derivative of that function is equal to the derivative of the integral, which is just f of x. So this is going to allow us, we're going to really be doing some substituting with this, and I'm sure your book video goes into a little bit of a deeper explanation and understanding with this. But basically, when you take the derivative of an integral, they're going to undo each other, and you're going to be left with the function that's inside the integral. There are some other things you have to keep in mind, especially if you are not going from a to x, a being some constant value. You have to consider using the chain rule, what the derivatives of those would be as well. There is a proof in your textbook on page 302 to 303. And again, that's going to say that every continuous function of f is the derivative of some other function, namely the integral from a to x of f of t dt. So if we find the integral using fundamental theorem, part A, the derivative of the integral from negative pi to x of cosine of t dt, again, it doesn't matter what the value is on the bottom of your integral as long as you have a regular x on the top. Derivative of the integral undoes each other. You're going to be plugging in whatever's on the top for the x value. In the bottom, that would just give me a constant. The derivative of that is 0. That's kind of why that goes away. So this is merely going to equal cosine of x. Part B, again, I'm going from a constant to a value. Take the derivative of the integral, they undo each other. You end up with 1 over 1 plus x squared. Notice I'm just replacing the t with the x. So that starts off pretty easy, but then we have a few other things that are going to happen that we need to be aware of and look at. So this one, find dy dx if y is equal to the integral from 1 to x squared of cosine of t dt. So we're taking the derivative of both sides here. Your book goes through an understanding of this about the chain rule, and I could rewrite this as a u, but basically what you need to take away from this is that if I'm doing the dy dx of both of these, I'm going to end up with cosine of x squared, because that's plugging in the top value, but I also need to multiply by the derivative of that bound. So this is actually equal to 2x times the cosine of x squared. And again, your book has a better explanation for why you need to multiply by the derivative of that upper bound. Just know that that is something that has to happen. Example 3 takes us a step further. Part A, we actually have to use one of our derivative rules from the previous section. Part B, we're also going to be using one of those rules, although Part B has a little bit more to it. So with Part A, this is not in proper format. Notice again, I'm finding the dy dx, but my x needs to be on the top instead of the bottom. So in order to switch that, I need to put a negative out in front. And then I can use my rule. I can plug in the x. I'm going to have the negative out in front there, so this is negative 3x times sine of x. And that's all I have to do for that one. because again, I'm taking the dy dx of both sides. Now b, I have a variable in the bottom and a variable in the top, so we have to split this apart. So I can split this apart. You can pick whatever constant you want. I'm just going to go ahead and pick 0. So this is the same thing as the integral from 0 to x squared of 1 over 2 plus e to the t, plus the integral from 2x to 0, because notice where one ends at the bottom, the other one has to begin, or I guess you could put the 0 first. It doesn't really matter, but it's split apart there. And then 1 over 2 plus e to the t. I need my dt's in there. So the first one is good. We'll go through and we'll plug that in, take the derivative of the x squared. However, the second one has my variable in the bottom instead of the top, so to switch that, I have to put in a minus. And again, I gotta get those dt's in there, don't want to forget about those. Now I'm to the point where I can actually plug in and multiply by the derivative. So when I plug in the x squared is going to go in for the t. The derivative of x squared is 2x. Well, when I multiply that fraction by 2x, I'm going to get a 2x on the top. For the second one, I'm going to plug in the 2x where the t is, take the derivative of the 2x, multiply it, it's actually going to be on top, so I'm going to have a 2 on the top over 2 plus e to the 2x. And that's really the most complicated type of question that you'll see with these. It really doesn't go much further than that. So that brings us to example 4. Find a function y equals f of x with derivative dy dx equals tangent x that satisfies the condition f of 3 is equal to 5. Well, we know that the derivative has to equal tangent, so I could set up some integral like this, because when I take the derivative of the integral, I should end up with tangent as long as there's an x at the top of that. So that satisfies the first condition. Now the second condition says that f of 3 has to equal 5, which means when I plug in 3 for x, I would have to get back 5. Well, I don't have anything on the bottom of my integral right now. I don't have a value for a, and I did that on purpose because I want you to think about this for a second, especially going back to those rules that we had in 6.3. If I want to plug in 3 and make sure I get back 5, I probably want to have some kind of 5 in the problem. Because if I take the derivative of that 5, it's going to go away. Derivative of 5 is 0. So that's not going to affect the fact that dy dx has to equal tangent of x. But in order to guarantee that f of 3 would equal to 5, I would have to make this integral value, when I plug in the 3, equal 0. The only time an integral equals 0, well, not the only time, but one of the times that we know of, is when your a and your b bounds are the same thing. So if I let the value on the bottom be a 3, and then plug in a 3 for the x on top, from 3 to 3 of tangent of t dt, that would just be 0, and I would be left with 5, in fact, whenever I plug that in. So this is kind of a way to get around writing an equation, especially if you don't actually know what your antiderivative is supposed to be. And this is a tool, I believe this comes up, I think in chapter 7 as well. So this is something that you will see again about using the integral and this part of the fundamental theorem in order to get some type of equation when you don't know the antiderivative. So in chapter 7, we will learn about how to rewrite this solution. There is a little bit more that's involved with that. You actually have to do some substitutions, and that's why we can't quite take this approach yet. We are not doing this exploration. It is in your textbook if you want to go through and take a look at it. This is where I'm going to stop the first video because the next slide is going to pick up with the evaluation part of the fundamental theorem. So we're going to do all of those examples together. So go back through, watch this video. Remember, this is the antiderivative part, not the evaluation part of the fundamental theorem of calculus. And reach out to me if you have any questions at all.